Okay, so we resumed our discussion on geometric set cover. I would like to recap the algorithm that we did yesterday, and we had just about started the analysis, right. So, what was the algorithm? Okay, what was the problem? We have a geometric range space with some bounded VC dimension. Okay, so I think so given some ranges and given a set of points x, and we want to cover all those points x. Let me just write it. So, the problem was given this range space x comma r, where number of points is n, number of ranges is m, we want to find a subset, let us say r prime of r that covers all points of x, and as small as possible, of course. The smallest side is often known as the optimum set cover, okay. Smallest cover is some opt, okay. So, this is the smallest number of ranges that will contain all the points of x. Okay. That is known to be a intractable problem in the general case of a set cover, and it is also known to be intractable for many of these geometry cover problems, right, including the covering of points by disks. We want to avoid the cost incurred by a generic set cover algorithm, which is in polynomial time. We can find a set cover of size approximately opt times log of n. So, this is just using a greedy approach of the set cover, right. You start with the set that contains the largest number of uncovered points, okay, include it, okay, update your the points covered, okay, and then look at the next set that covers the most number of uncovered points, and you go on till all points are covered, and that is your greedy algorithm, and that achieves this bound, okay. And surprisingly, using even more sophisticated methods, which are more complicated than the greedy method, we still can't obtain a faster algorithm, okay, in the general case, okay. For special cases, as people know, like vertex cover, or where your sets have bounded sizes, etc., you can get better approximation bounds. Now, in our context, again we don't have such restriction, okay. Again, these are sets, it can be arbitrary large sets, but they have this property. So, S has bounded VC dimension. Most geometric set cover problem will have this property. So, exploiting this bounded VC dimension, we want to get a set cover which is superior to this size, namely it does not have we do not want any dependence on this n, okay. N is a number of points. We want to have something that is a function of only opt, okay, maybe log of opt or something like that. So, this is the algorithm that we were discussing yesterday. What do we do? For some epsilon, let us we will define what epsilon is exactly. So, for some epsilon, we pick a epsilon net. By the way, so this problem, this set cover problem works in the dual range space, because we are trying to cover points by ranges, and we are going to use epsilon nets, okay. So, normally when you define epsilon nets, you do a random sample of the points, okay, but here we are covering the points using the ranges. So, we are going to random sample the ranges. So, we will look at the dual range space, okay. So, we will look at S star. So, whatever we are doing is basically with S star, okay. So, we are working on S star, and S star we are saying has, let us say, a shattering dimension. Now, I am not using the VC dimension, I am using shattering dimension. Again, there is a relationship between VC dimension and shattering dimension, but for simplicity of calculation, we will just use shattering dimension bounded by this delta star. Okay. And the subset that we are picking from this dual range, okay, will be a sample of the ranges, and that sample of the ranges is basically done by this epsilon, the technique of epsilon net. So, we are going to construct epsilon net, and we keep constructing this epsilon net, okay, with it's a weighted epsilon net. Okay. So, we begin where all elements have unit weights, and then we revise the weights, okay, and we keep revising the weights and picking up this epsilon net, and every time we pick up this epsilon net, we actually test whether or not it covers all the points. Okay. The moment it covers all the points, the algorithm stops and says, okay, this is the cover, right? And the size of the cover is as we will see is what we were looking at, namely that it does not have that log n factor. Okay. So, let me just again quickly step through this so that we can do the analysis. So, it repeatedly selects an epsilon net for some epsilon of S star. We are working in the dual range space which has shattering dimension delta star. So, we choose an epsilon net. Now, we are talking about choosing an epsilon net in the weighted sense, okay, because initially we start with weight equal to 1 for every range, and then we revise depending on which ranges we prefer to pick up in our epsilon net, because certain points. So, if it is not a cover, okay, what happens? So, first of all, you pick up this subset y, which is the epsilon, which is supposed to be epsilon net. Okay. If it is not an epsilon net, then you discard it. Okay. You do not even look at it any further. Okay. You first verify whether it is an epsilon net. How do you verify it is an epsilon net? You basically just brute force verify it is an epsilon net or not. Okay. So, look at all subsets of, so we have m subsets, right, or m ranges, okay, and n points. So, we brute force look at that. So, whatever time it takes n times m, it is a polynomial. Okay. So, we look at that, verify whether it has hit all the large subsets of size at least epsilon n. If it is not, then we discard it, do not process it further. But if it is an epsilon net, then we examine y with respect to whether or not it is actually a cover. Okay. So, it may be that the one that we discarded may have contained a cover, but we discard it nevertheless. Okay. So, because the probability of not being an epsilon net is less than half. Okay. So, whatever we do, even if you only consider those samples that are epsilon nets, we are missing out maybe a factor of 2 in the process. It will be much easier for us to analyze only those samples that are actually epsilon nets. Okay. That is why we do not even retain or consider those samples that are not epsilon nets. So, only if it passes the test, we go to the next step, and the next step is verify if this subset or this epsilon net covers all the points of x. Okay. Now, if it is covered, then you stop and output, okay, which means that essentially this epsilon net y of the size delta star over epsilon log of delta star over epsilon is the size of the set cover. Okay. And you can see that this does not have any, well, we do not know epsilon really, maybe epsilon has some dependence on n, we have not defined epsilon yet, okay. But let us assume for the time being that epsilon does not have any dependence on n. So, this is the size of the set cover, okay, which is only dependent on the shattering dimension, which is a property of the range space, and epsilon that we are choosing carefully. Okay, but if it is not an epsilon net, what do you do? If it is not an epsilon net, if it is not a cover, then you check whether so you find out some point that is not covered. Okay. So, there has to be at least one point, let us say p, that is not covered by this set of ranges. Okay. And so, look at all those ranges that contain p. Okay. So, that we are denoting as R sub p. So, R sub p is a set of all ranges that contain the point p. Now, one of those ranges must be also present in the optimum set cover, because in the optimum set cover the point p must be covered, and the point p can only be covered by one of those ranges. Right. So, what we are doing? So, now we do not know which of those ranges is in the optimum set cover. So, we blindly sort of increase the weight of all those ranges in R sub p by a factor of 2. So, we double the weight. Okay. So, that what we are doing is, so that with sample next time we are actually preferring that at least one of those ranges get picked up by my sample. So that the point P is covered next time, right. And so we just keep repeating this process. We pick a sample, okay, of this epsilon net size, okay, check whether it is an epsilon net, if not discard. So we process to see that if the set of ranges y actually covers all the points. If so, we are done. If not, okay, we look at which points it missed out, pick up any of those arbitrarily pick up any of those points, look at all the ranges that contain the point, and for those ranges we double the weight. Okay. So, in the process what happens that every time we fail to pick a set cover, okay, we are certainly going to increase means what, double the weight of at least one range in the optimum set cover. Right. Every time we miss a point, at least one range that contains the P must be in the optimum set cover, and since we are doubling the weight of all the ranges, so even that range will double its weight. Okay. So, certainly every time we have to repeat the optimum set is certainly gaining very rapidly in weight. Okay. So, the whole idea is that so therefore, very soon we should basically stop, because if this we can't go on forever, because this the weight of the optimum set is really doubling, and since it is doubling, it is going to sort of dominate at some point, and we have no choice. The sampling algorithm will have no choice but to actually output that set or something that is very close to that set. That's the intuitive idea. Okay. But when we do the rigorous analysis, what is happening is we are making we do one more change, okay, and that is we will double the weight. So, we don't double all the time, we double only when the weight of this ranges that contain the point P is less than epsilon w. Right. And the reason I gave for that was, see, if since it is an epsilon net, okay, if the weight was greater than epsilon w, okay, we would have certainly covered P, right, because the weight of those ranges that contain P exceeds epsilon w. So, my epsilon net must hit one of those ranges. Okay. So, only if it is less than epsilon w, okay, we will double. Because if it is greater than epsilon w, in any case it would have been picked. So, because it is an epsilon net and this point P was not covered, okay, it means that the weight of those ranges is less than epsilon w. Okay. So, when we double the weight, what are we doing? We are increasing the weight, the total weight of all the ranges by at most epsilon w, right. So, this will help us analyze, right. So, every time we double the weight, we are increasing the weight by no more than epsilon w, which is basically 1 plus epsilon multiplicative factor of the entire weight, right. So, therefore, Wi is less than or equal to 1 plus epsilon Wi minus 1, which is basically this quantity, and so we will carry on from here. Okay. So, this is one way of bounding the weight, this is upper bounding the weight. So, the weight at the ith stage of all the elements put together is no more than 1 plus epsilon to the power I. Okay. So, now let us continue with this calculation. So, the other way that we want to bound the weight is when we double. Okay. So, here is another observation. Let us say, let me use some number where elements, let me take some value. Let us say what is it, let us some beta times. Okay. Then the and in some set A. So, A is the set of elements that we are doubling the weight at every time we double, we have the option of picking one element of A and doubling the weight. So, when we have this option of picking up any arbitrary element and doubling, the claim is that the least. So, and after a while we look at what is the total weight of all the elements. Okay, suppose all the elements started with weight 1. We are doubling, picking up an arbitrary element, double, put it back, and again double, put it back. So, the claim is that the least weight is obtained when the doubling is kind of spread across evenly across all the elements. Okay. Then the least total weight is obtained when the doubling is spread evenly across elements. Okay. So, you can actually formally prove it, but let us say that you have just 2 elements, let us say A and B. Okay. So, well, not 2 elements, yeah, we have only 2 elements. So, example, it is in 2 elements, okay, and we double 2 elements E1, E2, we double A plus B times. Okay. Then verify that 2 to the power A plus 2 to the power B is greater than or equal to 2 times 2 to the power A plus B by 2. Can you verify this? Yeah, you can check it. But I think even in this example you can probably verify, right? Okay, so I am not going to give a proof of this. Do you want to put in some figure and check? A equal to 3, B equal to 3? Huh? Yeah, right. Okay, so you basically extend it to any. I mean, you are right. Actually, A, B, kind of equality. So you extend it to the other elements. So what it implies is that when we look at the set of elements in the optimum set cover, okay. So among other elements, those elements could also be increasing their weight, right. What we are claiming is that this algorithm, as we run more and more iterations of the algorithm, okay, the elements, or sorry, the ranges in the optimum cover, okay, some of them are going to double their weight, okay. And this one claims, this observation basically says that after, let us say, running it some t times, okay, what is the minimum weight gained by the elements in the the ranges in the optimum set cover, right. So, if we run, let us say I iterations of the sampling and doubling, so there are k elements in the optimum set cover. Okay, we will make an assumption that we know k. If we do not know k, we will see what to do later. Okay. Suppose the optimum set cover has size k. Okay. So, suppose k what is the minimum weight of the elements in opt after I iterations? So, according to our previous observation, it should be, if you spread it evenly across all these elements, that should be the least, right. So, it will be so each of the k elements should be doubled I over k times, right. I am missing some floor and ceilings, so do not worry too much about that, right. Do you agree with this? Okay. So, this is the minimum weight of this, right. We also have from the previous lecture an upper bound on the weight, right. So, I can write less than Wi must be greater than this, because this is the weight of the, it is just the weight of the elements in the optimum set cover. There are other elements also. So, this is certainly lower bounds that. Okay. So, this must be, so this inequality must hold. So, Wi, which is, well, we are saying it is 1 plus epsilon to the power I times W naught. W naught is the initial weight, which is each range has weight exactly equal to 1, and we have m ranges, right. So, this is again equal to 1 plus epsilon I times m, right, and we can upper bound this by something like e to the power epsilon m I times m, right. 1 plus epsilon is less than e to the power epsilon. Okay. So, now we just have to solve this. So, that will give us some bound on the number of iterations. So, if you take log on both sides, so it may be, so let us just just to make calculation easier, suppose I equal to k times q or some such thing. So, then we can rewrite as k times 2 to the power q equal to e to the power epsilon. Can you just tell me what the solution should be if you take log on both sides? So, this will be log k plus q equal to m plus Well, I am missing some constant factor. This is E, so this is 2. So, there is some constant factor that I am missing here. I am just being a little sloppy. So, what does it say? I is okay. Should we get I is less than, or I should get greater than? Oh, right. So, where am I getting? I should not have I should have. You are right. Yeah, I thought there is something that we are not writing correctly. Q. We're solving for Q, right? Not I. So, it should be, yeah, that is what we want. We want right. Okay, now what this says is that Q should be less than or equal to something. For that inequality to hold, we can't go on forever, so we must end somewhere. Okay, Q can't be too large. Right. So, we have, and for this to be positive, now you can define your epsilon, right. So, as long as epsilon is less than 1 over k or something, this left hand side will be positive, right. So, then we can basically have a solution that Q is less than or equal to. So, by let us say now we can choose epsilon, right. So, we have not chosen epsilon till now. So, suppose we can choose epsilon, right. We are choosing the epsilon of the epsilon net. Suppose epsilon is equal to 1 over 2 k, right. Then Q is less than or equal to order of log, okay, 2 times or whatever. Okay. So, this says that we will end in some finite number of iterations. Number of iterations is bounded by k times q, right. So, number of iterations. Well, it is not quite the number of iterations, it is the number of doubling steps. Iterations where weight doubles, right, is less than or equal to k times q, right. So, is order k times so, m is the number of ranges, okay, and k is the size of the optimum set cover. Well, how did I choose epsilon if I do not know k? If I knew k, then I can choose epsilon to be this, right. And I have to know epsilon because I am picking an epsilon net for some known epsilon, fixed epsilon. So, if I knew epsilon, then my total number of iterations is this quantity. If I knew that, if I could somehow choose epsilon to be, actually if I choose epsilon to be less than 1 over k, then itself we are going to converge. But how do we know epsilon? Which epsilon are we going to use in the original algorithm? The algorithm is very simple. Choose an epsilon net for some epsilon. If it is not an epsilon net, discard. If it is an epsilon net, see it is a set cover. If it is not a set cover, then double the values of some ranges that contain the uncovered point P and keep on going. So, the size of the cover is fixed. The size of the cover is this. Now, we know epsilon also, right. So, the size of the cover is delta star, epsilon is, let us say, if it is 1 over 2 times k. So, the size of my cover is delta star times k log of delta star times k, that is the size of my cover. So, size of cover, if we knew how to choose. Is order delta star times k log of delta star times k. Now, in this quantity, delta star is the shattering dimension of the dual space, does not depend on n. K is the size of the optimum cover, right. This is the size of the optimum cover, which you do not know really. Okay. This is the shattering dimension. S star. So, we have succeeded in our goal that we have a set cover whose size does not depend on, does not have that logarithmic factor, log n factor, right. It only depends on delta star, it only depends on the optimum size. So, this log is could be much smaller than log of n, right. That was the goal, log of. Why? See, delta star is the shattering dimension, right. That is a fixed quantity, that is a constant, right. So, we have something that is basically big O of opt of log of opt, right. So, you can think about it like big O of opt times log of opt instead of opt times log of n. So, the only missing ingredient here is that how do we choose epsilon? I do not know k, epsilon is some 1 over some 2k or 1 over 4k or some such thing. Will it make a lot of difference? I am just wondering. Suppose we choose epsilon to be equal to 1 over 4k instead of 1 over 2k. Will it make any difference really in the asymptotic calculation? It is again just constant, right. So, does it give you any idea?
Some other strategy.
And what strategy? What will be the simplest strategy? Greedy what?
Find a greedy solution and.
So, one is that you guess the size of k, right. I mean, I can try for k equal to 1, 2, 3, k will be something, right. I can try for all kinds of k. I can try for k equal to 1, 2, 3, 4, whatever we want, right. And k has some bounded size, the optimum size is k is certainly less than or equal to n, right. That will be one way of achieving it, okay. Maybe not a very smart way of doing it. So, we know that k is less than or equal to m. This is the size of the range space, this is the number of ranges in the optimum So, this is true. Okay. So, I can start with k equal to 1, 2, 3 and run this algorithm. Okay. For every value of k, run the algorithm and pick the one that gives me the best size cover. And by this we are guaranteed that the cover size is not going to be more than this quantity, because for the right value of k it will be this quantity. For any other value of k, if it is smaller we accept it, if it is, and that is all, and it cannot, certainly there will be at least one term if we try for all values of k. So, the minimum of that cannot be more than this. So,
K is small, then the algorithm won't converge in the I. And we get the lead term.
so you are not, if you do not converge after some so what you can do is, so if it is not the right value of k, so you will run it for some constant times whatever value of k you have chosen times log of this. If it does not converge, give up. Okay, so let me write it down. Okay, for the guess k equal to ki, we try order k's of I, that log iterations. If it does not converge, it does not terminate, we know that it is not the right value. So, we are only trying to guess the value of k, and from our previous observation, if we can guess it even within a factor of 2, we are done. So, why should we try out all values of k? We should simply try out k equal to whatever 1, 2, 4, just double. If you do the doubling trick, you will converge much faster. So, you are going to be within a value of within a factor of 2 very quickly, within whatever log k times, right. So, that will save the whatever, it will make the running time much better. But even this one is trying for all values of k is also a polynomial time. It is also polynomial time. After all, we are only looking at polynomial time approximations, but this is a much faster and better scheme. So, that is basically the full description of the algorithm. Okay. The algorithm is very simple. You just sample a certain number of elements according to the bound of the epsilon net, sample uniformly at random, but you have to do the weighted sampling because your weights are going to change. So, the only non-trivial part of the algorithm is to implement a weighted sampling, but even that is not very difficult. So, once you do the weighted sampling, you keep doing it and you get it. Any questions? Okay, so whatever we discussed actually is a fairly general scheme. What are we doing? We are doing the following. There is some hidden set, okay, that we are trying to find. So, the hidden set is basically the optimum set cover here. Okay. The hidden set could be, let us say we are trying to solve linear programming. Okay. The hidden set is the set of those constraints that define the optimum. In D dimension, we know that D constraints or D hyperplanes define the optimum, right. Somehow we need to choose those D hyperplanes. Okay. So, you can use a very similar approach there, that you what do? You choose epsilon net of some size, according to the the linear programming has its own VC dimension, etc. You choose them, you compute the optimum of the sample, okay, and then you find out if that optimum satisfies all the other constraints. So, there has to be, whatever we are doing, there has to be a check whether or not we should terminate. The termination condition in the case of set cover was that whether it covers all elements. The termination condition in the case of linear programming is that whether or not the optimum of the sample is actually the optimum of the entire thing. Okay. And we just continue like this. So, if it is not optimum, there has to be some violating constraint. Okay. So, then you are going to double basically the weights of the weight of all those. So, here you are going to double the weight of of all the hyperplanes that don't contain that point. Okay, so there is there's some optimum we computed for the sample. Okay, there are some hyperplanes that violate that optimum. So clearly, one of those hyperplanes must be in the optimum. Okay, so we again just double all those weights, and we keep doing this. Okay. So in this particular algorithm, we will again at some point, once we pick up all the optimum constraints in the sample, then the optimum of that sample, okay, is going to satisfy everything. See, there are d optimum constraints, right? And if you have somehow picked those d optimums in our sample, the d optimum constraint in the sample, and we compute the optimum, that has to be the optimum of the entire set of constraints. So here the hidden set is the d. Okay, again we are going to do this doubling trick, and after a certain number of iterations, we are going to find the optimum which will satisfy everything. Okay. So what we get in the end is the true optimum. Okay. There, of course, the critical thing is how many iterations do we require to find that. So it requires some non-trivial calculation. And again, the state of the art of linear programming is such that it's not really polynomial time, because there is no what is called no strongly polynomial time algorithm for linear programming. Okay. So this method that we are using will give you something strongly polynomial if it succeeds. Okay. So because there is no, it's an open problem whether or not there is a strongly polynomial time algorithm for linear programming, but it gives something that is let us say better than what is known by other methods. Okay. So this doubling trick works there also, and there are many other applications of this doubling trick.
The ellipsoid algorithm for linear programming is perhaps polynomial time.
No, they are polynomial. They are not strongly polynomial. So the difference between polynomial and strongly polynomial is that, if the number of iterations of this algorithm does not depend on the size of the numbers. So linear programming, in the constraints what you have essentially each hyperplane has some coefficients, right? So whether it's Kacchian's algorithm or whether it's Karmarkar's algorithm, the running time is proportional. So to not only the number of constraints that you have, the number of constraints, let's say, is n. Another parameter is the dimension. So n d. Okay. So fine, it's going to be proportional to the input size anyways, right? I mean, input size meaning the number of coefficients that define the problem. So n is the number of coefficients in each constraint. D is the number of coefficients in each constraint because d is the dimension. N is the number of constraints. So if you have something that is just polynomial in n and d, okay, n squared d to the power 5 or something, okay, then that is polynomial time, strongly polynomial. Okay. But if you have some algorithm that behaves as following: n square d to the 4 and L to the 10, where L is the size of the coefficients, number of bits in the coefficients. So of course, L is the number of bits in the coefficients, so that must be counted in the input size. So if you look at the definition of polynomial time, it's fine, it is still polynomial in the input size. So this is absolutely polynomial by that definition. But the strongly polynomial time algorithm definition is that it should not have dependence on the size of each number. So whatever be the size of each number, the number of whatever, the running time of the algorithm should be immune to that. Okay. So if I am using larger coefficients, then I am going to pay some more price for it, because when I multiply, when I add, it's going to be more. But then the convergence of the algorithm should not depend on that. So simplex, by the way, is strong, but not polynomial, right? But it is strongly what is improved. Very, very strong properties have improved recently, right? I mean, it got the Nevelina award actually this year. So you have a situation where you do what is called a smooth analysis. So earlier, what was known is that on the average, simplex is polynomial. Okay. Now, what is averaging done over? Averaging is done over, all possible instances are equally likely, and that is an assumption that which is too strong, and no one. Why should we make that assumption? So that assumption is not neither valid, probably not desirable, but at least there was a result, it was a deep result that in that case simplex is not only polynomial time, it's very close to linear. And then about 7-8 years back, it was shown that some variation, strong variation of the average thing, that is, you take any instance of linear programming, okay, and you average in the neighborhood of that instance, okay. So, you give me any arbitrary instance, okay, and then I am allowed to average over a neighborhood of this instance, okay. So, I take some epsilon, I perturb the input by some amount, that there is a parameter, let us say some epsilon neighborhood, okay, and if I allowed to perturb it over this epsilon neighborhood and look at the average running time in this neighborhood, then that turns out to be polynomial, okay. So, that is called a smoothed analysis. So, that holds for that is a notion of analysis which is called smoothed analysis. So, we are looking at something close to worst case, but not quite worst case, because you give me an instance, that instance may be very hard, okay, but I am then allowed to look at a neighborhood of that instance, and I do my averaging over the neighborhood, and whatever instance you give me in the neighborhood, it is polynomial time. That was shown for linear programming, okay, and that result got what is called the Nivellini award, which is the highest prize given to theoretical computer science scientists. So, that is known for linear programming, but then again it is not a strongly polynomial time, it is some, and it is something like I do not know, maybe a 120 page proof or something like that. Not pretty. These are essentially what we are saying, these are numerical analysis based methods. Anything that is these are using linear algebraic techniques. So, they are all linear, they are numerical analysis kind of analysis, that you have to look at the convergence of the matrices where the size of the numbers really matter, right, all those things. So, that problem remains open. Anything else? So, we have more or less ended what we wanted to cover, at least all the basic problems that we wanted to address. In the next couple 2 or 3 lectures that we have left, I think Professor Agarwal will talk mostly about some higher level application of these things, to other areas like maybe graphics or image processing or things like that.